Hey everyone, and welcome back to our live development sessions here. Today we're going to do something different yet once again, and we will look at operating systems. And specifically, we will be looking at file formats. And in this instance, it's the binary format of an operating system's binaries. And in particular, we're interested in converting the a.out format that is used in Plan 9 as it is used in Plan 9 over to ELF, the executable and linkable format. So yeah, I've already opened up a few things here, and we will actually start looking at a specification here coming from GNU that is called Multiboot. And Multiboot is a specification for operating system images so that they can be loaded by bootloaders. And that is supposed to be very, very portable, so all the specifics of any given operating system don't matter. And that allows for having very, very flexible bootloaders that can be loading any arbitrary operating system image, but the actual image format can still then be, investigated by the specific tools of the specific operating system. So that would mean that you would have multiple headers. And let's actually see how that works. So the page I've opened here is the page on the OS image format, well, or the section thereof. So as you can see, we're somewhere in the middle here. So there is a scroll bar, right? So this is a very, very lengthy document actually. And so let's see what it says here. OS image format. An OS image may be an ordinary 32-bit executable file in the standard format for that particular operating system. Let's just neglect that we also have 64-bit systems nowadays. Except that it may be linked at a non-default load address to avoid loading on top of the PC's I/O region or other reserved areas. Let's also neglect that we might not necessarily talk about PCs. However, for today's purpose, PC is just fine, and we're not going to talk about specifically what that actually means. Let's just take it as it is for now. Anyway, of course, it should not use shared libraries or other fancy features. Yeah, well, that makes sense for an operating system's kernel, right? So when you boot into a kernel, then you can't yet make use of anything like shared libraries, right? Otherwise, you would need to put another bunch of burden on the bootloader, and yeah, that wouldn't make sense. So the idea is that you just load one image file, and that would then take care of everything else by itself. An OS image must contain an additional header called the multiboot header, besides the headers of the format used by the OS image. And yeah, that is what I just talked about earlier, right? So having multiple headers in one image means that, we can use various parsers and they would still understand the same image just in various ways. And yeah, so the idea is to have this one portable thing. The multiboot header must be contained completely within now the tricky part, first 8 kilobytes or 8,192 bytes of the OS image and must be long word, and that would be 32-bit aligned. Yeah, never mind those specific expressions here. Word just refers to a specific size of a numeric value. In today's systems, we mostly use bytes which are 8 bits, and 32-bit would then be well, it would be a long word in that instance. So we would say a byte is the 8 bits, then 16 bits is what would be called a word, and then 32 bits would be a long word, and 64 bits would be a quad word. It's just, weird naming for all these different things. Anyway, in general, it should come as early as possible and may be embedded in the beginning of the text segment after the real executable header. Which means, so if we have the real header, like let's say we have an ELF file, you would have the ELF header first, and then the multiboot header, and then everything else. And that means for the operating system's image format, we need to have something that allows for inserting this multiboot header somewhere here, right? So yeah, this is a should, right? So should means you don't have to do this. But still, we have a must here. So the must is over here. you will see this kind of wording actually in lots of specification-like documents. Anyway, so that's what we need to distinguish. We always need to fulfill the must, and the should is a strong suggestion so that, we come up with certain conventions in a way. Anyway, what does this mean, text segment? If you don't know about operating systems binaries, well, text is just because, things have changed over time. Back then, the idea of text was that would mean that is the actual program code. So when we read text segment here, think of just code. This is where the machine code would be, right? Okay, so now the question is, why are we looking into this? Well, I ran into this because I was at the international workshop on Plan 9 just last week. And I tried to bring up a Plan 9 kernel. And I tried to do that by loading it from a Linux environment. And Linux understands a bunch of binary formats, and that would namely be ELF. You can have something that starts with a shebang, when you write those scripts. That's configurable in the kernel. And in theory, you can also read a.out. So those are the natively supported formats by the kernel. However, that a.out, I think is not actually the same as the Plan 9 a.out. So a.out is not too specific, right? And we will also have a look at Plan 9's a.out in a bit. Anyway, so what we can also do in Linux is, instead of having the kernel parse the binary, we can also do that in user space. And we have a bunch of programs for doing that sort of stuff and libraries. And namely, that would be in an implementation that is called uroot, uroot being the universal root file system. And there we have a parser that also understands the Plan 9 a.out format. It was just a bit broken over time, so the parser itself was actually just fine, but the integration was a bit broken. And that's because when we try to parse a binary, the problem is it can be any of a handful of formats. And if you don't have fallback options set up the right way, you might accidentally not be able to parse something that would otherwise be just fine, Anyway, so yeah, now you have a bit of a background story. So let's have a very, very quick look at the Plan 9 a.out format, which is actually documented on 9p.io. So 9p.io is one of the main websites of the Plan 9 projects. So Plan 9 being the research operating system from Bell Labs. If you start at the main website, you will actually get a bit lost. So I will quickly show that to you as well. So let's just go to 9p.io. You still see that old image here from Alcatel-Lucent. They at some point, held the rights to the operating system, and then Bell Labs, was sold a bunch of times, eventually to Nokia. And at some point, they actually released the operating system Plan 9, and we now have it under the umbrella of the Plan 9 Foundation. But there is also like a bunch of derivatives. So we have, a handful of projects dealing with Plan 9. And first and foremost, there would be 9front. If you go to 9front.org, this is where you can actually find a more modern implementation with downloads that you can use right away, specifically on x86 systems. You can install them actually on your PC, or you could also download an image for Raspberry Pi. I think Raspberry Pi 1, 2, 3, and 4 are supported, and then a handful of others. Like the famous MNT Reform laptop, for example. Those are the machines that the developers actually use. And yeah, you might also want to fiddle around with that. Anyway, so back to the a.out format, and let's zoom in a bit here. So this is the man page. If you have read a classic Unix man page, you might be familiar with this sort of format, right? It's really just text, so you don't have visual graphics to assist you. Maybe sometimes there is ASCII art or something, but in general, it's really just pure text. So you need to, get used to that format if you want to digest that, or have somebody that explains it to you in another way. Anyway, so this is how this format roughly works, and I'm just reading the description for you here. So there is a header file which actually describes this format. That would just be a.out.h. Makes sense, right? So .h being from the C programming language, it's just the way that declarations are separated from implementation. So in C you have these header files, and then you have the .c files, and you need to glue them together manually. So for each and every C project, you need to create a build system as well. Anyway, so it says an executable plan 9 binary file has up to 6 sections, which means it's fairly simple, right? So we got a header. That makes sense because that explains the format and the layout and everything, like everything we actually want to know. Let's say the metadata. Then we got the program text. Again, the text means it's the actual binary code. Then we've got the data. So the data would be, something like, let's say, strings in a program, for example, right? So they're not executable code, but if your code is being executed step by step, at some point, let's say you want to print out a string, then you would load that from somewhere else, a data section, put that in memory, and then, iterate over it and output it to, it could be a screen or a serial port or something like that. Anyway. Then we got a symbol table. The symbol table means, it's like the names of functions and such things, so that you can, when you need to debug something, you could actually see, hey, we're now in this function at this offset here. What is the name of this function? Because the raw machine code wouldn't actually contain that information anymore. So we need to have a way to trace that back. And that's the symbol table. Then we got the PCSP offset table. That is only for specific older processors. This year, you might have seen this at some point. This is the Motorola 68K series. So that is older processors from like the 80s and such. So yeah, you need to know the Plan 9 operating system was actually started by the in the late 80s. And beginning of the 90s, they actually made the first public announcements and releases. And then finally, a PC/line number table. I'm not sure what PC actually means here. I think it would be program counter, and SP might be stack pointer. So yeah, that's also an artifact of the past, right? So in the past, there was this issue that there wasn't really much space for many things to store. So, sort of everything was kind of abbreviated. And the abbreviations, when they pile up, it's really hard to memorize all of them. And the next issue is they might actually collide. So you get, multiple abbreviations that, or the same abbreviation that resolves to multiple meanings. So yeah, in order to understand this sort of stuff, you need to do very thorough research sometimes. But yeah, we don't really care too much right now because we're interested in converting file formats at some point. And yeah, we'll also get back to that in a bit. Anyway, now comes the interesting part because that is what we need to convert. The header given by a structure in a.out.h, this header file, contains 4-byte integers, and then very importantly, in big endian order. A big endian is about the order of the bytes. Big endian means, when we write down a value, let's say we've got a 32-bit value, we can write it in 4 bytes, right? So yeah, let's just do this real quick. So we take our favorite editor here, being NeoVim. You might of course also use I don't know, Acme or nowadays Z editor or something. Anyway, so we're writing a number. So for hexadecimal, we use this sort of notation. We write OX and then the rest of the digits, right? So let's say 1, 2, 3, 4, 5, 6, 7, 8. I will now split this up a bit and look at it this way. So we have 2 digits now grouped together. 2 digits are 1 byte each. And 1 byte is, what many processors can address just like that. So you can read a single byte from memory, or you can read a 16-bit word from memory, or you can read 32 bits at the same time from memory. And now it gets a bit funny. So the way this sort of stuff would be stored currently in the most modern machines, or most of the modern machines that we have, is in little endian notation. And little endian means we've got the lowest bits, or well, in this instance, the lowest bytes first, which means in the memory it actually looks like this. So we get 7, 8, 5, 6, 4, 5, no, 7, 6, 7, 8, 5, 6, 3, 4, 1, 2, 1, 2, like this. Okay, so arguably that would be in reverse order, but it also means if we want to read from a given memory address, let's say this is memory address 0, okay, now we read the first byte this year, that would actually be the lowest byte, so this year, right? If we read 16 bits, well, now we can just concatenate them, right? So we take this byte, and we get this here. And so on for 32-bit values and 64-bit values, potentially 128, but yeah, let's not care about that right now. Anyway, so just very roughly, this is little endian, and it would be big endian if it would actually be the same thing as here. Which means you need to be careful with this now. And if you take a given file, you now need to know if you start parsing, you need to know the endianness of the numeric values. Anyway, let's put that aside again. All right, so here we get the corresponding struct, and the struct is called exec. Exec for executable. Once again, very old times, they didn't have much space to spare. You could only punch as many holes in a punch card and such things. You only had like, I don't know, a few megabytes and then kilobytes of memory, and so on and so on. And yeah, in the 90s, they were still a bit more careful with the space. Nowadays, we don't care, right? So we got gigabytes of memory, terabytes of storage in our laptops already. So yeah, we can actually spell things out conveniently. Anyway, so let's see what's going on here. So we got this struct definition, and in C it's just like this. So you would say struct and then the name of the struct, and then for each of the members of the struct you would first declare the type and then give it a name, and then comes a semicolon. And you do that for each and every row. And the first thing here is a so-called magic number. That is also a very common term used for all sorts of binaries. You will see these magics all over the place. We'll also look at a different example in a bit. It's not necessarily a number, so sometimes it can actually be human readable characters. The idea is just that you have something which gives you an indication of, hey, this is actually now the format that you expect. So you get a few bytes, and those bytes will tell you, hey, everything else that comes hereafter is as you should expect it for the given format that you use. Which means if you open a file and you read something which is not that magic number that you expect, then you can error early and say, hey, this is actually not the format I was expecting, so I'm not going to continue here. Which does not rid you of sanity checks, right? You should still check the values that are coming thereafter. So let's say you have an image file, for example, and we actually looked at that in another live stream that we did here when we looked at the security of firmware, right? So I was just writing a superficially large number as the image dimensions into a bitmap file, but it was way past the actual size of the bitmap file. So we actually had a small bitmap, which was just like I don't know, some tiny image, and I said, well, it's, I don't know, 1 million pixels high or something, right? So yeah, always do those sanity checks. Anyway, in this instance here, we got a few more things. So we got our text. We already talked about that. That is the actual program code. We got data. We got BSS. This is the uninitialized data. I actually don't know what the abbreviation is for. I forgot that. Doesn't really matter for us anyway. So we got sims, that is short for symbols, the symbol table that we briefly talked about. Then we got entry, that is the entry point. So that is the start of the executable. Then we got SP size and PC size, also again abbreviated here. And now it gets a bit tricky, and I don't really know why they did that. Sometimes they claim to be clever about things, but yeah, I don't know what the reasons would be to do this sort of stuff here. So first of all, the magic number here is not a fixed magic number, but they actually use a different one per machine architecture, so the processor architecture, right? So for example here, the Motorola 68K would have its own magic and so on. But they don't just define a specific number for each and every one of them right away, but they actually do an operation on a number, and that works as follows. So you actually take two numbers, and they make up the magic value. You don't really see that here. We will talk about that later in a bit. This here is the simplified version. So here you would just take one number for a start, and this is processed by a macro. So in C, this is how you write a macro. So you say define, then you give it a name, and if you are familiar with the notation of functions, that should actually be very familiar to you. So this is the the input. So we got a b here. So b would be a value, and then we would multiply it by 4. We would add 0 to it. I don't know why they have these, this plus 0 in here. I mean, it could be that they wanted to use other numbers for some purposes at some point. But yeah, it's like a no operation, right? So we can just omit that. They would multiply by b again. So it's actually 4 times b squared here, and then plus 7. Okay? And now we would do this for all those sorts of architectures, and as you can see, they all got different values. Well, starting at 8 for whatever reason, then we got 11, 12, 13, then another gap, 16, 17, and so on. And we're currently looking at AMD 64, so the 64-bit x86 architecture, which is not in this list here. And why is that? Well, this is an older copy of the man page, and we will actually look at the current one in a bit, well, or the actual header file. Anyway, so this was just for a brief introduction so that you can roughly see how this is made up. Yeah, and then you will also see this is currently just based on one value. I will show you something that is based on 2 values. Anyway, so they got more explanation here on how those symbols work. So they also have a struct. For whatever reason, they don't provide a name here, and so on. All right, so we get this format, and we want to convert that to the ELF format. And ELF is the executable and linkable format. So that is also something coming from Unix. It's used in many Unix and Unix-like systems, also on Linux, for example. The BSDs are using that, and so on. And they also have a magic number, and it's actually here on Wikipedia. The magic number is the hex value 7F, which is not an ASCII character, and then the ASCII characters E, L, and F. Just ELF. Simple as that. I don't know why they put this here. I mean, they could just have done something else, but whatever. I guess they just felt like it. Yeah. And the layout is a bit more complicated, as you can see in this graphic here, which I'm not going to enlarge too much because, I mean, just from a quick glance, you can already see how much this is, right? I would just quickly zoom in a bit. So this is now the hex view of such an ELF. And yeah, you can see like there is a bunch of stuff in here. So yeah, let's not deal with that too much. Let's just zoom out again or whatever, close it, because we don't really need to care too much. I will now show you something, and that something is a comparison between 2 binaries. And they're actually the same binary. And one of them would be this one here, an a.out file. That's the file that was given. And here's another copy with the .elf extension, and that is actually a.elf file. And if we look at it, we can actually see it. So we get the 7F here that we also saw on Wikipedia. Then comes elf. And now you might wonder, hey, why do we get the 7F here and elf here? So this is the hexadecimal, this is the ASCII representation. Well, I just aligned it that way so that we can actually compare left and right. So if you look, Green here means that is something only on this one side, which yeah, if you compare the two, you can see this is just a bit of a larger header, and then red means something that is different on both sides. So like this value, for example, so we got 0, 0, 0, 0 here, and here it's 8A97. Anyway, so yeah, if we were to scroll down a bit more, you will see that this is almost the same thing, except for one tiny bit, and that is down here. By the way, I'm using biodiff here. Biodiff is a diff tool, and that allows me to compare two binary files, and with the space key, I can just jump to the next difference. And you can see that here, this value is different from that value. But I think that is actually not correct. I think if I do another alignment, I should actually line up the same again. What's the key again for align? It's F3. Oh, look. Yeah. So, yeah, this is actually the same. I had to align a few times in order to, see that they are in fact the same file. So, yeah. Yeah, now we got a better alignment again. Now you can also see, yeah, this versus that. Which means, like, if we cut this file at this offset here on that side, or this offset on that side, we would actually end up with the identical file again. So we're just interested in the top part here. Okay, so let's remember what we had in the a.out documentation. So the first 32 bits, being this here, they would actually identify the platform. And our target platform, as I said, is AMD 64. So now we need to figure out what would AMD 64 actually look like. And lo and behold, this here is now a checkout of the 9front repository. And in the 9front a.out header file, I'm reading something a bit different. First of all, I've got this here, HDR magic. Yeah, that is just another value that we, concatenate with our given values, or rather, we use the OR operation on the numbers. So we take this here, hex 8000, and the magic macro that you see down here is now a bit different from what we had on the older website. This actually takes two inputs. As I said earlier, this would be F and B. So F here would be the header magic used, for example, down here where it says AMD 64. We take HDR magic, and then we take the number 26. And 26 means we now need to do this operation again. We say 4 times 26 plus 0, again, times 26 plus 7. And let's use our favorite calculator to see what the result would be. I actually have that in my history still. There we go. Right. So I was using this here. I mean, we can also go that way. We can say F equals hex 8000. So we just do the same as the macro. We take hex 8000, and then we say B equals 26. We say 4 times B plus 7, and then we just print this out as a string. And the result is, lo and behold, 8A97. With the preceding two zeros, that would be 00008A97. And let's look at the biodiff again. That's actually what we got here. Okay, so that worked. So what I did was, so far I started writing a parser for this. And what we've got open here now is our favorite editor, and I've started writing a program in our favorite language. So in this language here, we can actually, we don't actually have to create like a build system or something. We don't have to mess with header files, it just works. And what we do here is, well, because this is now an application to help us, I'm creating a small command line interface, and I'm using the library named clap for it. Clap as in clapping your hands, or CLAP for command line argument parser. Yeah, the way it works is very simple. So you just define, an enum here for the commands that you want to have. And I've started with 2 commands. I want a convert command so that I can say, hey, take this file, convert it to this other file. Well, take an a.out file and convert it to elf, right? Or just parse the file, right? So read in a file that is in a.out format and print me whatever information you have. And that information could then include like, let's say, well, first of all, the header, of course, right? So it would tell us the header, and then we could print, let's say, the symbol table, for example, and stuff like that. There are existing tools for that, of course, on Plan 9, but here I am not on Plan 9, so I wanted to have something that I can also use on my host operating system. Anyway, so yeah, very simple. In both cases, currently I just take one argument. I just take a file name, right? So I'm reading the file then, and then yeah, I will try to parse it or convert. Convert is not yet implemented, so yeah, that's a to-do for later. Anyway, so let's start with the parsing. What I'm declaring here is actually based on the man page that we just saw, but we should also say see this page and 9 front. So a 9 front, what was the file again? Would be this here. Sys include a.out.h. All right. So that gives us the struct. So the struct here is still the same, right? The only thing that really changed with 9 front is the new magic values that have been added for the new architectures. So yeah, in elf it's a bit different. In elf it's always elf, and then another field would then tell you what architecture you actually want to run on. And I see it's getting a bit dark here, so let me turn on some light. Oh well, how about that one? Looks like it's gonna rain outside. Yeah, not the most perfect of lights, but what do you do? Yeah, I can already hear the thunder. Alrighty. And let's now see what we've got so far. So we've got the struct, right? So we got the magic in the beginning. Then we got the text size, we've got the data size, the BSS size, everything that we also saw, except I already spelled it out here. So, spelling things out, helps the reader a bit more to actually understand what it means. Yeah, we can actually drop the size off here because we already encode size everywhere in the name. And yeah, so we get some notes here. So BSS is the initialized data, text segment. This is the binary code segment. Then we got the initialized data. So yeah, this is like strings and so on. Uninitialized is stuff that you will use then at runtime. Yeah, and all the other fields here. And what I have so far is this is how we process the commands. And we'll just look at the bottom one here. The parse command will take the file name. I'm just printing the file name here. I'm reading in the file. And then I will try to read the a.out struct from prefix. This is coming from another library that we're using. That library is called zero copy, and that easily lets us, just define our data structure, and then, we can use all these very helpful functions like, read from prefix. Read from prefix means I will give you a bunch of bytes, and from the very start, you will try to read this as if it were the struct, and then we get an instance of that struct to use. Which means we can now say take the magic, for example, right? So we got a.out.magic, and then we can say, hey, if it's this, then you output that. And now you might see I actually reversed the bytes here. And why did I reverse the bytes? Well, because this is now the little endian representation. Remember that our numbers are written in big endian. All right, so you can already see the result here. So the above here, I will just run it again. I'm doing cargo run, right? And then I say I want to use the parse command, and then I give it the file to read. And yeah, it prints out the file name again. It gives us the architecture, in this instance AMD64, and then we get the text size. I'm also printing that. Yeah, and everything else, I'm just printing the whole struct again. Now you might see something, if you're familiar with Rust, you might be a bit confused. So I'm using U32 here. So U32 means an unsigned 32-bit numeric value, except I'm using uppercase U. And this uppercase U also comes from our library that we use for parsing, the zero copy library. And we can see that here above in the import. So we got zero copy byte order. And byte order defines, the big endian numbers as uppercase U32. Yeah, there is also like little endian. Then there is, special ones for like network packages, for example. They have their own notations and so on. Yeah, but I don't know exactly what is in there, but yeah, there is a bunch of helpful things. Anyway, so yeah, that's how we get that information. And I actually just started creating a repository here. Let me just do another git add again, and then commit this as our first initial commit parse a.out file. All right, we don't have a remote yet. So as you can see, I haven't yet set up a repository. So let's do that. Let's add a remote, and we just call it, well, origin. That's the common name that Git also uses. And we will go github.com, and we will put that in the platform system interface project. And yeah, I just call it P9 a.out to elf. It's a bit of a stupid name, but yeah. Anyway, we cannot push to this yet because it doesn't yet exist on GitHub. So let's do that right away. So we go to GitHub. This is now my GitHub, and we go plus new repository. And this repository is under platform system interface, getting this name, and the description is parse and convert plan9 a.out binaries. All right, this is a public repository, of course. No README just yet. We'll write one at some point. And we add a license. What license do we use? Well, let's just go with GNU public license version 2. Very simple license. I put it out there. You can do with it whatever the heck you want. If you distribute modified copies, you just also need to publish your changes. That's roughly it. I think that's a very sensible license. We could also go with MIT. Should we do that? Should we go MIT? We could also do dual license, but it actually defies the purpose of GPL. Let's just go MIT. That's also a commonly used license, especially in the world of JavaScript and also in the Rust ecosystem. Yeah, so that one means you can actually do whatever the heck you want, sort of. You don't need to provide back any source code. So yeah, that's that allows for actually proprietary products. But yeah, here we don't care. It's not like this is anything critical or anything, right? So we fetch that remote, we fetch origin, and we rebase, but the branch is then named main. Righty. So what we just did is we created a new repository. We added the repository as a remote. We are fetching what we got on GitHub. On GitHub, we already got the license checked in, and I just rebased on the license. So we got this here, initial commit down here. That one is created by GitHub, as you can see. Commit is no reply at github.com, and it created the license file. That's what we just set up. All right, so copyright platform system interface. That's our project name, right? Anyway, and then we put our stuff on top. Initial commit parse a.out file. Both are sort of initial commits. Anyway, so let's go push this. Go push git push u origin main. So that just means track the upstream that is behind a remote named origin and the branch named main. Excellent. You see these paw footprints here. That means I got untracked files here. And let me show that to you. If we go git status, you will see there is 2 untracked files, and that is actually, you know, the a.out binary and then the elf copy. So, you know, I just copied that over so we can fiddle with it. Well, in fact, this is actually just the same as this here for now. Yeah, we will also take the other elf that we got and see that we, you know, end up with the same result when we do our conversion. So the other one was from building on a Plan 9 machine that could output both the a.out and the elf file. Now we want to have a conversion tool that we also run on other machines which are not running Plan 9. Anyway, so we're this far now, and let's actually see. I don't want to really, you know, so we really need to have the headers, right? So let's see that we get only the headers and nothing else. So what I'm gonna do is I will copy the .elf file here as well, okay? And then I will see that I cut out only the headers, right? So I don't want the other stuff. And so from the elf, we would get everything up to A0. What is A0 in like decimal? So this is 160 bytes. So I just go dd and I take the elf file. I will take a block size of 1, right? And I will use a count of 160. And the output file is then 9pc.elf.header. Okay? And we do the same with the a.out file, and we can actually go this way, right? That makes it a bit easier to distinguish. So how much do we need to copy here? Well, now it becomes a bit tricky. This goes up to hex 28. Hex 28 is 40 in decimal. So yeah, it's just a quarter of that size. All right, and then we move this to .a.out. Alrighty, let's do a quick check if everything is as expected. So this here is the a.out header, ending in 8011 and then 4 zeros. Is that also what we got here? Yeah, that's how it ends here. And the elf header is then this here, and the last line is the one that contains a 4 here and then lots of zeros. That looks just like this line here. Okay, so far so good. And how about the multiboot header though? So multiboot is saying that you know, ideally the multiboot header should come just next, right? So can we also extract the multiboot header? Well, let's look at the header layout. The header layout is like this. We got, again, a magic. We got flags, we got a checksum, header, header, that's address, load address, load end address, BSS end address, and so on. Those now depend on flags. Right. Yeah, it's a bit weird, but it looks like, yeah, we have 48 bytes, right, in total. Yeah, just judging by the offset here. All right. What is the magic? Why is there no? How do I get to this definition here? Header magic fields, right? The field magic is the magic number identifying the header, and it should be 1B AD B002. One bad boer. I don't know what that's supposed to mean. Boo 2. One bad boo 2. Yeah, it looks funny. Do we find this? Do we find a bad boo 2? Okay, let's search for it. So we also got the hex dump down here, right? So this here is now the let's just take the a out. It doesn't really matter which one we take, right? Because they should be the same. And I'm using xxd here. So do we see one bad somewhere? No. That was just the line number. Okay, endianness. Do we see AD1B? Oh, there we go. There we go. This is our magic value. So we got the endianness again, right? So it's 1B, AD, B002. And this is after the 0018, 0090. In very much the beginning. So let's see again here. So if we look at this view, it looks like we got it somewhere here. Hang on. Yeah, now we gotta read a bit carefully. Oh, hang on. No, I was looking at the wrong file. We need to look at this here, right? Okay, we're looking at the a.out file. So this here. So we had hex 48 bytes first, right? And 48 is 72. Hex 48 or 72. And hex 48 would here be, oh, there we go. Okay, so that means we have these two other lines here. I don't know what this is, but it's good to know. Anyway, so yeah, we have a multiboot header down here, and we can see what else should we have? So we should have the flags, we should have the checksum, and so on. Yeah. Okay, so yeah, we do actually have a multiboot header. Why is this interesting? Well, I tried to just run the kernel in QEMU, and we can actually also do that now to do a quick check, right? So yeah, let me just do that. I have my QEMU command here still in my history, and I was using the 9pc64.elf. And as you can see here, it looks like nothing is really happening, right? So yeah, it's a bit weird, but I'm using no graphic. And instead of no graphic, oops, gotta reset that. Instead of no graphic, we will actually use graphics now. So we get this funny window, and here you can see plan 9, and something is coming up. It's having trouble now finding a drive for its root file system and such. But yeah, that doesn't really matter to us. It is coming up, right? And we can now do the same with the a.out file. And lo and behold, well, we get the same thing. And well, that is because, well, apparently QEMU is parsing the multiboot information. And it actually says so here. It says Multiboot knows VBE, we don't. Yeah, it's a bit weird. So this should be uppercase B. There is no period here. And what that means is, well, we can also supply something. We can say dash VGA stood. So we get a standard VGA something. I think that's how it works. Oh well, we still got this message. Yeah, let's see in my history. What did I do? No graphic. that's something else again. Yeah, whatever. Um, yeah, we're not going to play with this much more anyway. Uh, yeah, I just wanted to show you that we can in fact run this here somehow, and then we should see something. Um, but yeah, one thing I want to be able to do is I want to be able to look at the obj dump, right? So if we go obj dump, then we can now look at the symbols and such and do disassembly and so on. And let's do that on the elf and see what happens. Oops, that somehow didn't work. I assume this elf is actually not a correct elf. We can also go read elf, and see what we get here. So this actually looks okay. So we got two sections, load, and then null, another section. Here you can see this is readable. I think the E should be executable. And then here we got readable and writable. So that would probably be the BSS section. And then this here is probably just the data section. I think so. Well, that's the elf. What did we get here? Oops. No, not help. I want to parse. I want to parse the a.out file. What did we get here? Oh, here's the thing, right? So with the plan9 a.out file, we don't actually get offsets, but we get the sizes. And let's see about the sizes if they make sense. Okay, we get the text size 158666, and that's exactly the same number that we see down here. Let's see about the data size. Data, same size. Okay. Then we get the BSS size 747E8. Oops. This here is a bit less. I don't know why that's the case. Oh wait, that's actually the other number. That's the symbol table. Okay, so we sort of lost the BSS information. Maybe, I don't know. Might also be that you need different arguments to elf, read elf. So the elf format, yeah, it's a bit more complex. So it's not that simple here. Let's look at the man page for read elf and see what else we can get. Oh, great. So we just did -l for the program headers. We could do the -s for the section headers. And there is -e for just headers. I don't know what that is. And then we got -s for symbols. Okay, let's go and print out the section headers. Oh, no sections in this file. Oops. What were the symbols? Dash lowercase s. Do we get the symbols? Oh no. Dynamic symbol information is not available for displaying symbols. I would assume that we actually need to translate this symbol table somehow. But yeah, I don't know. I'm actually not that familiar with these formats myself. So yeah, this is very much of an exploratory endeavor here. What else can we do? We can do... all right, yeah, we got -e for just headers, right? Maybe it prints all the headers. Oh, look. It also prints the elf header itself. So we get the magic. This is the elf magic, right? The 7f and then ASCII ELF. Class is elf32. Yeah, data notation in Little Endian and so on. Version 1, so yeah, I think there is only elf version 1 so far. I haven't seen... Have I seen version 2? I don't know. The ABI and operating system, well, Unix-like, System 5, ABI version 0. The type is it's an executable, that makes sense. It's an AMD 64 binary, version 1 again. And the entry point, oh, look at that. The entry point address is the same as the one up here, the same one that we also parsed. Then we got the start of the program headers, 52 bytes into the file. And the start of the section headers is 0 bytes into the file. Then we got flags. There are no flags. The size of this header is 52 bytes. And then we got the size of the program headers, another 32 bytes, and 3 program headers. So these are the program headers here. If it's 3 of them, Is that like 32 bytes each? I don't know. Huh. Anyway, we got three program headers. Funny. What else do we got? Number of section headers, 0. Right, section header string table index is 0. So yeah, I actually did a Google search on converting this, and I got this weird summary here from the so-called AI, and it says you can't directly use a tool to do the conversion. Well, of course I can. I just need to write that tool. Instead, you need to recompile the source code, yada, 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 or use a tool. Now it's a contradiction in itself, like convert that translates a plan9 a.out file into a compatible ELF format. And apparently, Anand Narayanan has written about this. Sorry for messing up your name here. At some point. I also did a search for that, but couldn't really find it. I've just seen the name on the mailing list a few times, but yeah, I couldn't actually find any mention of that convert tool whatsoever. There is, however, a convert tool that we use, quite a bit, but that is for converting multimedia files. So yeah, that also reads in binary data essentially, and also parses headers and stuff, but it's not meant for this sort of stuff. You can use it, say, to, I don't know, convert a PNG to a PDF file or something, or I don't know, whatever, JPEG to a bitmap or something. Alrighty, so now back to this here. The question is, what do I need to do to create one header from the other? So now that we got just the two headers here, we can also just look at those, right? So we don't need to look at anything else. We just want to translate this here. We want to translate this here to that. That would be enough for a start. So I don't really care much about the symbol table right now and so on, right? So I just want to have the above header. Okay, so the good news is there is already something in the Rust crate. So there is a Rust crate for parsing elf, and I think it's called Goblin, if I'm not mistaken. Elf parser. Elf crates.io. Elf parser. Simple elf parser. Elf lib. Rust parser. Elf kit. Rust elf parsing. There is only 100 of those, as it seems. Another one. Okay. Yeah. 10. That's very funny. So 10 is German. The number 10. Get it? Because elf is the German number, the German name for the number 11. So 10 comes before 11. Stupid. Anyway, I actually like that wordplay. Okay, so I think Goblin is the name. Yeah, Goblin. Funny. So yeah, this handles elf and dwarf and other files. So dwarf is another file format again. Oh look, it can even read Mac-O. That is used on the Darwin operating system, which is what macOS is based on and such. All right, alrighty. Yeah, features, awesome crate name. Yeah, I will give you that, awesome crate name. Okay, good. So let's cargo add Goblin. And where is the documentation? Alrighty, so the documentation says it's a library and it can parse elf. Okay, great. Let's actually do that real quick. Okay, yeah, let's see. We could extend the parse command to be a bit more smart, right? We can see if we can parse something as elf, and if we can, then we fall back to this here, right? Can it actually parse a.out? No, it cannot parse a.out. So yeah, let's do this. So we import goblin object. Okay, we also get goblin error. Right, that's for the result type here. We don't really care, so we just use goblin object. Okay. So we will do the following. If let, okay. What do we get here? Okay. Oh no, we don't. Okay. We actually do the match here. What do we do? Okay, we do okay. No, we don't do okay. We need to do the match. So yeah, it could be anything else. We're just can we actually say if let some elf? Does that work? If let some object elf equals, what do we do? Object parse of object parse. We give it a reference to our binary. And then we do this here, and we would return. Oops. And we go okay. So this would be an early return. And we just print it out. Does it work? Cargo run. So we go parse, and then we give it the elf. Yeah, it just takes a bit to compile. Oh look, Rust is a bit unhappy about this. Oh no, oh no, oh no. We found option. I think this needs to be okay. Awesome, that works. Okay, so if we get an elf, we just print out the elf information, and otherwise we just continue. Okay, great. That worked. Okay, but we don't actually want to parse. We want to create an elf now. So how do you create an elf? What do we got? Modules. Elf 32. Huh. Oh, can we? Does object actually does that provide us with a method to create an elf? Elf. Can we just go elf new elf, show 25 fields? Ew. Look at that. Do we have helper functions to create this? Like create an empty elf? We got parse. Whoops. There is from. Yeah, it looks like we need to write our own elf by hand in a way. Oh well, so many fields. So many fields. Okay. Okay. Let's do the following. So I will add this now to my convert command up here, right? So again, we're reading in a file and we parse it as a.out, and now we create an elf from it. Let elf equals goblin elf. Okay, and now we need to fill the fields, okay? So it's missing header. So what do we need for header? Header needs to be header. And that has another, damn, so many fields. And yeah, this is where elf gets a bit more complicated. So we have, I don't know why everything is prefixed with an E, but that's also what you see on Wikipedia. Yeah, it's a very lengthy thing. So yeah, we got ident. I don't know if that's identity or something. I don't know what it refers to. Oh yeah, it should be. Hang on. No, it's 16 bytes. 16 bytes. So it's not just the .elf thing. Hang on, but that's how it should start, right? Huh. Okay. Anyway, so we had program headers, section headers, and so on and so on and so on. Can we just, yeah, let's do that. Let's just create an empty header here. So we need this here. Yeah, this will now get very ugly, but what do you do? Okay, so we go let h equals goblin elf header. We got all these fields. So yeah, we need a u8. Let's say we just take 16 zeros, okay? Then the type. The type is a u16. I don't know. Let's just go with 0 for all of them for a start and figure out what values we actually need at some point. Yeah, it might be that there is, oh, might actually be that header has a method for it. Is there like, oh, look at that. Ah, there is new. Okay. We can go header new. New. Okay, that's intriguing. What do we need to provide for new? We need to provide a context. I don't have a context. What is this context? We need a container and we need endian. What is container? Little and big. That's also endianness. Huh, weird. Weird. Yeah, let's just go with little for both of them. Okay, so we need a ctx. And ctx again is at ctx equals goblin elf header ctx. Okay, what did we need? We need container and LE. LE is it is already called little endian. Okay, so we got container container goblin elf container. That's an enum, right? Oh no. Can we just go little? I'm afraid that's not how it works. I'm afraid that's not how it works. Okay. Can we go from? Oh, great. So you can take a container and convert it to another container. How do you create a container? Huh. Funny. No, these are the trait implementations. Auto traits, blanket implementations. Well, variants, little and big. Enum container. Okay, let's look at the source. The size of a binary container. Let's just see what happens. Okay, so we got container and we got LE, goblin, elf, LE. Oh, do we need to do this here? Does that work? How do we do the other thing? How do we do endian? All right, so we just go endian. Elf, endian, little. Oh no, endian is private. That's the issue here. Okay. Consider importing this unit variant instead. Goblin container endian little. Wait. Goblin container endian little. Like this. We also have container here. Let's do this here. Does that work? No. CTX is private. Okay, so this is probably just internally used by the parser. So we resort to creating the header manually. And header equals. Okay, back to the original plan. So we got the fields here again. So we go with 0 u8, 16 of those. Take 0 here. I copied something without the comma. Oh well. 0 and 0. This is a bit boring and tedious, right? Uh-oh. How did that sneak in? Okay. So, header. Header is not enough. Yeah, just put the comment here so Rust doesn't reformat this. Or the editor, whatever. Okay, so we need all the other stuff. Okay, so we need program headers. What is program headers? Elf. So this would be a vec of program header, right? So we can just go and say this is a vec of program header. We can just use 0 headers and we're done. Uh-oh. Damn. That's not how it works. How very unfortunate. Can we do this here? Program header. Does that work? Oh, I can just go empty vec. Rust is smart enough about it. Okay. Okay, so we got section headers. Also an empty vec. Noise. Okay. And then we got all this other stuff. Come on. Stir tab. Whatever stir tab is. String table? Structure table? I don't know. A common string table format, which is indexed by byte. Okay, actually read that. Indexed by byte offsets and not member index. Constructed using parse with your choice of delimiter. Please be careful. Huh. Maybe we can actually find a library that creates an elf for us instead of like parsing it from a given file. Rust elf crate. I mean, there were other elf crates, right? A pure safe Rust interface for reading elf objects. No, I want to write it. Huh. I want to write an elf. Elf RS. No, this is also for reading it. Great, so there's 100 parsers for elf, but no writers. New. This would get a file. Library to generate elf binaries. There are loads of libraries on crates for parsing elf. I want to generate an elf binary. No clue which is best, but fairy is used by Creton. So would be what I'd look at first. Okay, let's look at that. Fairy. Emitter. That's what we're looking for. Oh look, hasn't been maintained in 4 years. Excellent. How complicated is that? First, we declare our symbolic references. It is a runtime error to define a symbol without declaring it first. And we now define our local functions and data. Okay, this is inline binary code, but whatever. And link. We declare our relocations. Oh my. I really just need to write the new header. I don't want to, pass around all of this stuff. I mean, nah. Okay, back to just writing this stuff ourselves. Okay, we can, what can we use as the delimiter? From slice unparsed, get unsafe, parse, new, pre-parsed. Do we get fmt? Yeah, so we might be able to just use an empty byte slice here. Get unsafe from slice unparsed, or just new. Okay, so what is the difference between new with the bytes in the delimiter and what was it? New pre-parsed bytes and delimiter. Yeah, let's just go new. Okay, so yeah, let's just do that here right away. Let s equals stir tab new, and we give it a vec and a 0. Okay, and that needs to be a reference. Excellent. So we need the stir tab, the section header string table. So this could be S, and we don't just use S, we just use a we use a clone of S. Can we do this? No method named clone. Seriously? Seriously though. Okay. So you just use S. And the next Dynster tab, dynamic string table. And of course this, does this work? This shouldn't work. There should be an issue with references, shouldn't it? Yeah, we'll figure it out once we filled out the rest. Okay, how's it with the dyn_sims, a sim tab? Sim tab. An elf symbol table. How do you create one? What are the definitions of sim tab? Sim tab. There we go. So we got, oh, we actually have a default. So I can just use default. No. What was it called? Sims is a sim tab default. Look at that. Just do the import. Okay. Awesome. Can we actually go stir tab default? Ah, that also exists. Nice. Is there an elf default? That e equals goblin elf d. No, it looks like that doesn't exist. Oh no. Well, is there a default header? Do you have a default? No. Too bad. Okay. What else do we need? You can go away. Okay, we need the so we got the sims, the dyn_sims. Now we got the sims. We got the stir tab. Let's just, oops, put them in a certain order, right? So we got the dyn stir tab, dyn_sims, sims, section header stir tab. What else? Okay, so we need dynamic. Dynamic is an option of dynamic. An option means we can just go dynamic none. An option can be none. Dynamic relas, dynamic relocation sections. No, dyn_rels. Weird. I hate these abbreviations. Okay, what do we need? Reloc section. Do you have a default? Yes. Excellent. Okay. Relux. I have no idea what all of this stuff is. Could be platform something or PLT, page level, table, whatever. I don't know. Just weird stuff. PLT Relux. Another Relux section default. Then we got stir Redux. Stir is an empty vec. SO name. That's like something shared object name, maybe, I guess. So name is just none. Doesn't need it. The interpreter is also none. We don't need to interpret it. Libraries. Again, none. But like empty vec. R paths. Another empty vec. Run paths. Another empty vec. Oh dear. By the way, if anyone is writing in the chat, I'm not seeing that, to be honest. Oh, somebody says, hi there, I gather chat engagement is not a high priority. Okay, bye. Oops. Well, poor you. Cheap viewers on whatever website. Yeah, no. Can we ban those people? Whatever. I don't really care. So I'm not watching the chat. Sorry if anyone is writing and writing something interesting. Yeah. So we got run paths. Is 64 is not true. This is false. Is it a lib? No, it's not a library. False. What else? Entry. Oh look. We can finally use information that we got. Okay, so we had the entry point. a.out dot entry point into. Rust can be smart about it. Okay, what's missing? Little endian is a bool. For us it's true. What else? What else do we need, Rust? Come on. Versym, verdef, verneed. Versym. Okay. Versym, verdef, and verneed are all none. And what's missing? CTX. That is not in here. What is the CTX this time? Come on, we went all this way. Where's the CTX? It's this container and LE sort of thing again. That is a public struct. Okay. And we should be able to construct all of this. There is this pub enum container. Okay. In mod container. And LE is scroll endian. Scroll. What? Text, no run. I have no idea what I'm looking at here, but this looks like an ancient scroll. Oh dear. Okay. Let's just create this. Let ctx equals goblin elf ctx. Can't believe I'm doing this again. Then we can probably also just create the empty elf from whatever we had before. Okay, so what did we have? Yeah. Okay, we're missing. No, struct ctx is private. How can it be private? I thought it was public. Here it says pub, right? Oh, wait. This is not elf ctx, this is just ctx. No. ctx is under, oh, it's under container. There we go. Do you have a default? There is a default. Look at that. Oops. Then we can also say let elf equals goblin elf elf. What was it? From. And then we just give it a context. ctx. Is that how it works? No. Oops. Wasn't it like... Hang on. Okay. So, no, this is object. Elf. Where are the... There. Iter is object. Parse header. Lazy parse. Parse. There. Try from ctx. Try from ctx. Try from... Isn't there try from ctx? Whatever. We just go ctx here and we should be done. Damn. That doesn't work. Okay. That is very unfortunate. Thank you for nothing, Goblin. So, we do need to find another library for this. Or just write our own. Which would be very unfortunate, but what do you do? We don't even need too many fields anyway. We can just zero out most of them, right? Can't believe we're doing this here. We had fairy, right? We say obj. Can we just, without any of this stuff, just go obj and we're done? That should work. Okay, cargo, add fairy. Let elf equals fairy artifact builder new. Finish. Okay, we need to give it a name. Yeah, we take the architecture. Oh, can I? target equals target, and let name equals smart empty string. Uh-oh. Okay, this is from Fairy. No. Where does triple come from? Why is that not in the example? Docs. Where is search? Triple. 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 Of course, it's from the target lexicon crate. Okay, cargo add target lexicon. There we go. Oh no, it's unhappy about it. Mismatched. Yeah, so Fairy was apparently built against another version of target lexicon, and that was 0.11.1. 0.11, oops, 1. Uh-oh. Huh. Where is the from? From, no. Is it from? No. Just target lexicon triple. Let's search for it. Search. Triple. It's funny enough that it's called a triple, but it's actually not. So we got x86-64, unknown, 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 elf. So if you count this, you actually have 5 parts. Huh. From stir. Ah, yeah. From stir in current scope. No, method name stir found in no. We probably need to import this. What if we use this? Does that work? No. Where is the source? Triple. Ah, there we go. Use core stir from stir. That must be it. There we go. Now it works. Okay. Good. Good, good. So now we convert. We're not doing anything with the elf here. So how about we print on elf 02 hex question mark and this. All right, so we're getting a panic. Why are we getting a panic? This should not be panicking. There is no need to panic. Oh, yeah. Let's... Oh, yeah, because this part is not yet implemented. Let's put a and false here. Okay. Oh no, that's not how it works. If false. No, it no longer panics. Okay. Yeah, that's where it came from. So this is an intentional panic, right? Anyway. Okay, so above we got the empty elf now, and we're going to fill it up. How do we fill this? How do we put the segments in here and so on? I'm not seeing that. Okay, so we had something in the fairy documentation. And yeah, so we had declarations where we declare functions. Huh. Interesting. I somehow have the feeling that it would be easier to just write the stuff ourselves. Let's consider this another failed experiment. Funny though. Okay, let's do the following. Let elf equals elf. Okay. And we put a to-do here. We remove all the imports from Goblin. And oh yeah, this is coming from Goblin. Goblin. And we define our own struct elf. Apparently we can put a to-do in here. Anyway, okay, so we got struct elf. We got a magic. The magic is, we're gonna write it as a 4-byte slice, okay? So we get the magic. Wikipedia elf. There we go. I'm afraid this could take a bit longer. Okay. So we have, why is all of this called e-ident? This here is class, data, version. Here it's called data, and here it says it's about the endianness. Here it says class, and that refers to 32 or 64-bit. Weird. Okay, so we go magic class is a U32. Oh no, it's not. It's actually just a U8. Okay, so here we go. Whether it's a 32 or 64-bit binary, either way, it's 1 byte, 1 byte, 1 byte. Okay. It's not like there is too many variants, so that makes sense. Okay, what else? Okay, so data is a U8. This is really endianness. What else? Version is a U8. Okay, so we'll start with that part, okay? So we go magic. Magic is, was it 7F? Then we got the E, L, F. Okay, we got the class. This would be 1 or 2. 1 for 32-bit, 32-bit. Oops. Then we got the data is 1, data is 1, data is 1, a little endian. And then we got the version, and that would just be a fixed 1. Fixed. Huh, awesome. Okay, so struct. We do this here. Yeah, let's fire this up. So this would now be the result of a.out to elf. Right. So if let okay, a.out, then we go okay. And we need to turn our elf into a byte array. So we want the byte slice to be returned. Yeah, we just call it B. Else here, nope. Yeah, we'll think about the error message later. Okay, so we got you, we got you. What's wrong about nope? Oh, right. So we go to string. Alrighty, and we'll just do this here. We just derive everything, right? So the struct, oops, the struct will just generate the into bytes for us, and we go let b equals elf dot to into as bytes. There we go. Do it like this. What's wrong with you? And just go to vec. Expected, found. I thought to vec would return a vec, but apparently it's not a vec. Expected and vec. Oh yeah, we just added and here. There we go. Okay. And that can be written to a file. Yada yada yada. Okay. So we convert the out file. Oh, come on. Okay, so for this here, apparently we need to put b before the characters. Are you happy now, Rust? Nice. Okay. So let's see what the converted header is. Looks like this. Okay. Wait, hang on. That's what we just created. No, that's not what we just created. This is what we just created. So this is what we just created, and this is what we would like to have. I would say we're halfway there. Look, we already got the first 1, 2, 3, 4, 5, 6, 7. The first 7 bytes. All right, everything else will be left as an exercise to the reader. So we're just going to finish here for now, okay? Because we've already been going for, I don't know, quite some time. Let's see. Oh, it's been 1 hour and 50 minutes already. Okay, good. For whatever reason, 5 people are watching this here. Thank you to those watching. I hope it was interesting. I guess it was not, but I don't really care. Anyway, just for a recap, so yeah, today we were looking at the plan9 a.out format, and we were trying to create a tool to convert it to an ELF, the executable linkable format, which we've read up on Wikipedia here. And we looked at the Multiboot specification because apparently that's a more common binary format. However, I want to be able to use, I don't know, my opcopy, opsdump, and whatnot on Linux so that I can mess with the plan9 files. And Google isn't too helpful. And with that, take care. Thank you very much and see you another time. Goodbye.